Let's return to the Young's experimental set with two slits. There's again the source of photons here on the left, and now we have the photodetectors after each slit. We remember that when we fire the photon, we don't know which photodetector is going to be hit. This is because the photon position is not an exact point in space, but it is a wave function, square of which determines its probability distribution. But after the photon hits the detector, the position of the photon becomes well known. It is exactly where the detector situates. So in the terms of wave functions, the upper wave function of this slide becomes somewhat like the lower wave function of this slide, which has one sharp, narrow peak. Physicists call this process the wave function collapse, because this beautiful and mysterious thing from above becomes something usual and boring at first sight, as below. We now know from the previous lectures that this process does not destroy the initial wave function. The measurement does not alter the wave function. It alters the state of the observer, us, making us subjectively observe only this small part of the whole picture. Now, what is this sharp spike anyway? Is it a wave function? Well, this depends on how sharp it is. In practice, no one can measure the exact point in space with zero error. So even if we have some small width of this peak here, we can still call this thing a wave function, because we can calculate the integral of its square and see that it is finite. But mathematically, we are particularly interested in some limit situation, where this peak narrows up to zero, giving us the exact point in space, while getting higher and higher up to infinity. This limit thing is called the Dirac's delta function, which is not a function in the usual sense. And of course, it is not a square integrable function. And since this thing is not a square integrable function, it does not physically represent a wave function of some particle. Our interest in delta functions is explained by the fact that they form the orthonormal basis in the space of square integrable functions, which means that any wave function f can be represented via the elements of this basis. Well, yes, these delta functions don't even belong to our vector space of square integrable functions, but still they form the basis there. Rigorous proofs are not the subject of this course, so you have just to believe me here. And I just used the term orthonormal concerning this basis, but I did not yet explain what orthonormal means in this space. What is the length of a vector which represents a function, or what is the angle between two functions? I'm going to do this later. Now again, I want you to believe me. We can consider this basis as orthonormal. So our upper wave function f is somehow represented in the basis of delta functions. And after the measurement, in an idealized case, where we obtain the exact point in space, the wave function becomes for us a delta function. So the initial representation with the infinite number of delta functions collapses to just one basis element. That's what measurement does from the quantum mechanical point of view. It always transforms the wave function decomposition in some basis into just one vector of this basis. And this vector is chosen randomly according to the distribution defined by the initial decomposition. Let's consider a simpler example with a finite basis. The letters E with a subscript here denote the vectors of some orthonormal basis. The letter X denotes the initial wave function. And what is written here is this wave function's decomposition in that basis E. Small letters X with the subscript denote the coefficients of this decomposition. We can call them the probability amplitudes. Now, after the measurement of X in this basis E, we obtain only one vector EA, with probability defined by the square of the amplitude XA. Now let's take a look at this expression, which represents the decomposition of the initial wave function f in the basis of delta functions. It is not a simple expression to understand. First of all, since delta functions are not the functions in the usual sense, this integral is not an integral in the usual sense. For those of you who want to dig deeper into things, I tell you that this is a Lebesgue integral, named after the French mathematician Henri Lebesgue, who invented the way of integrating such things as this. So instead of the basis E, we now have the infinite continuous basis of delta functions. Instead of sum over the set of vectors, we must write an integral, since now our basis is continuous. And instead of xa, we write here f of a, which is the coefficient in this decomposition. Again, I don't expect you all to understand this expression here. The point is that after the measurement in the basis of delta functions, we obtain one delta function with probability defined by distribution f of x squared. Okay, it's time to repeat what we have just said. First, wave functions can be measured. Second, the measurement procedure can randomly give us different results. Third, the whole set of these different results form the orthonormal basis in the space of wave functions. Now, this is a very important point. We can measure different things about a particle. We can measure its position in space, its momentum, its polarization, its energy level, etc. But for any such measurement, the set of all possible outcomes form an orthonormal basis in some vector space where we consider the measured wave function. 4. After the measurement, the wave function collapses, subjectively for us, to one of these basis states. The probability for the basis vector to be chosen by the measurement procedure is defined by the square of the coefficient before this basis vector in the initial decomposition. This set of possible outcomes, which forms the basis in the wave function vector space and defines the characteristics of our measurement procedure, physicists call an observable. More precisely, it defines what physicists call an observable. But we are going to talk about this later on the week 4. Now, I suppose it has been enough learning for one short week. Let's take a rest and continue learning on the 3rd week, where we are going to discover qubits and how they correspond to everything we discussed here. Goodbye.